Okay, for section 5.7, we're going to be working with limits, but a special type that's going to use something called L'Hopital's rule. So one thing I want you to remember is we used to have these forms 0 over 0, infinity over infinity, and we called those indeterminate forms. So that doesn't mean that our limit doesn't exist. It just means that we have to do more work in order for us to calculate that limit. And so, for example, here, when we have the limit as x approaches 2 of x minus 2 over x squared minus 4, when I evaluate that at 2, I get 0 in the numerator, 0 in the denominator, and so I know that I have to do something else. And the thing that I can do, if you remember your limit techniques, is I could factor the denominator. And then I see that my x minus 2's cancel out. So then I'm really just evaluating this limit for 1 over x plus 2. And then when I evaluate it at 2, I get 1 over 4. So that was like a 0 over 0 type. If I look at this next example, this is an infinity over infinity type. If I evaluate the numerator, this is going to approach negative infinity. I'm looking at my highest order or highest degree term. 3x squared, that's going to go to positive infinity. And so I have negative infinity over an infinity. This is indeterminate form. But if you remember, for limits as x approaches infinity, we can use our top-heavy, bottom-heavy rules. And so we have negative 5x squared and 3x squared. Those have equal degree, and so I can just take the ratio of the leading coefficients. However, not all indeterminate forms can be figured out by algebra or using the top-heavy, bottom-heavy rules. So for example, if we look at the limit as x approaches 0 of e to the 2x minus 1 over x, that's going to give me 0 over 0. I could try to factor, it's not really going to help me. I could try to divide, that's not really going to help me. We can fall back on some other techniques. We could look at a table of values or look at a graph. So for example, here I can see on my table of values, these values appear to approach 2. Same thing on my graph, it seems that this is 2. However, we want to be able to do this without using a calculator. And so there's actually another technique that can prove this, and it's called L'Hopital's rule. And what it says is, if you have one of the two following cases, so if either my limit is 0 over 0, or my limit is positive or negative infinity over positive or negative infinity, those signs don't have to match, just two infinities. Then what happens is that my limit of that rational function is equal to the limit of the derivative of the numerator over the derivative of the denominator. This is not quotient rule. This is just saying the limit of f over g is equal to the limit of f prime over g prime, not that that's the derivative or anything like that. And so on the AP test, they're going to be really specific about how you work this out. When I'm evaluating this limit, if I see this as a rational function, I should automatically be thinking L'Hopital's rule. I don't know for sure if I can actually use it. And so what you're going to do is split into two limits. The limit as x approaches 0 of the numerator, and the limit as x approaches 0 of the denominator. So if I evaluate the numerator at 0, I get e to the 0 minus 1. E to the 0 is just 1, and so I do get 0 here. In the denominator, I can just evaluate at 0. If both of those are 0, or if both of those are infinity or negative infinity, then I can use L'Hopital's rule. If not, then I cannot use this rule. And so what this means now is, so I'm going to say, then I'm going to rewrite my original limit. And I'm going to set it equal to my other limit. And when I'm using L'Hopital's rule, when I'm doing the step where I'm taking the derivative, I'm going to put an h over the equal sign. I'm really just saying these are equal by L'Hopital's rule. So I take the derivative of the numerator, derivative of e to the 2x is 2e to the 2x, derivative of negative 1 is 0, all over the derivative of the denominator, which is 1. So I'm taking those derivatives separately. So what I really have here is just the limit as x approaches 0 of 2e to the 2x. That means I have 2e to the 0, which is 2. Notice that matches the answer that we had from the table and from the graph. So this just gives us a technique in order for us to be able to solve indeterminate limits. Some of these limits you could have solved using our old methods. So for example, number 1, I see this is just polynomial over polynomial. I could just factor the numerator and the denominator if I wanted to, or I can maybe try to use L'Hopital's rule. So I'm going to take the limit of the numerator If I evaluate this, I would have 12 minus 14 plus 2, that's 0. Denominator, also just 0. And so then I know I can use L'Hopital's rule for this limit. So the derivative of the numerator is 6x minus 7. The derivative of the denominator is 1. And then I'm just going to evaluate at 2 again. So 6 times 2 minus 7 is going to give me 5. I could have factored and canceled if I want, but you can see here L'Hopital's rule doesn't take much time. You just have to be careful to actually check this part out that you can use L'Hopital's rule. In number 2, I'm going to evaluate again at -3. Now, I'm going to do a little bit of lazy math here. I don't want to, I'm not actually going to write out the limits like I did, only for the sake of time and space. But you want to make sure if you're working on a free response problem on the AP test that you actually write these limits out like we did over here. So on AP, this is how you want to write it. Here, I'm just going to plug in -3, I get 0. Here, I would have square root of 9 minus 5 minus 2. That is also 0. So it checks out, I can use L'Hopital's rule. We actually did know how to do this problem without L'Hopital's rule. We had to rationalize the denominator. Everybody hated it. So here's an alternate method that you might like better. Derivative of x plus 3 is just 1. For the denominator, we have x squared minus 5, but it's the square root. So remember that's to the 1/2 power. Got to use chain rule here. So don't forget the derivative of the inside. And so let's simplify this a little bit before we evaluate. The 1/2 and the 2 cancel out. This -1/2 is in the denominator, which means I can move the x squared minus 5 to the 1/2 to the numerator. But I still have this other x down here in the denominator. One thing I want to point out to you, I only use this h on the step where I use L'Hopital's rule to find the derivatives, not where I'm saying other things are equal to that. So notice my h was only up in that step. All right, let's evaluate at -3 now. So I have square root of 9 minus 5 over -3. That's square root of 4 over -3. So I have -2 over 3. All right. For number 3, same idea. We're going to evaluate at -2. You can plug this in. You're going to get 0 and 0, so I can use L'Hopital's rule. Now again, you could factor that, but factoring cubics, not the most fun. So derivative of the numerator, 3x squared plus 2x minus 8. Derivative of the denominator, 3x squared plus 16x plus 20. If I evaluate that at -2, what I'm going to notice is I'm going to get 12 minus 4 minus 8, that's 0, all over 12 minus 32 plus 20, that's also 0. And so since I got 0 over 0, that tells me I actually have to use L'Hopital's rule again. If I get an answer there, then I can stop. But if I get another indeterminate form, I will have to repeat my process. So I have now 6x plus 2 over 6x plus 16. And now I can evaluate this at -2. And so I'm going to have -10 over 4, which is -5 over 2. Same idea for number 4. If I evaluate at 1, I'm going to get 0 and 0. It's pretty straightforward when you have polynomials. You just want to check and make sure you get the 0 over 0, because sometimes they can give you problems that look like they're L'Hopital's rule, but they're not actually. So you have to be careful not to use it when you're not allowed to. Okay, so if I evaluate this at 1, I have 20 minus 8 over negative 1 minus 27. So just 12 over negative 28. I can simplify that a little bit. I'd get negative 3 over 7. Okay, let's do some that are not just polynomials. Do a little trig, logarithmic, exponential, the fun stuff. So make sure you're studying those trig values. Always good to know. So here, limit as x approaches 0. Cosine of 0 is 1. So I have 1 minus 1 over 0 minus 0. That's going to go to 0 over 0. So I know I can use L'Hopital's rule. So my derivative is negative sine of x in the numerator over 2x minus 1. So if I evaluate this at 0, I have negative sine of 0 over 2 times 0 minus 1. This is actually an okay way to leave your answer on the AP test, but you have to make sure that this doesn't give you an indeterminate form. So sine of 0 is 0, but the denominator is negative 1. And so 0 over negative 1 is 0. So I can stop there. That's my answer. All right. Number 6. If I evaluate at 1, natural log of 1 is just 0. Minus 1 plus 1, that's 0. E to the 1 is e, minus e times 1, that's also e. And so I have 0 over 0. So I'm going to go ahead and use L'Hopital's rule here. So I've got 1 over x minus 1 all over e to the x minus this derivative e times x is just e. The derivative of a constant times x is just that constant. So when I plug in 1, I get 1 minus 1 over e minus e. That's going to give me 0 over 0 again, which means I get to do L'Hopital's rule again. So the derivative of the numerator is negative 1 over x squared. Derivative of the denominator is just e to the x. That e is a constant, so the derivative is 0. And now I can evaluate at 1. My numerator is negative 1. My denominator is e to the first, or just e, and that will be my answer. All right, number 7, this nasty looking problem. If I plug in 0, I'm going to get 0 over 0. Notice when I take my derivative here, I'm going to have to use product rule. And so I have 2x sine x plus x squared sine x, or sorry, cosine x. Got carried away there. All over 3x squared minus 2x. If I evaluate this at 0, I get 0 over 0, which means I get to do L'Hopital's rule again, which means I get to use product rule 2 more times. So I've got 2 times sine x plus 2 cosine x plus 2x cosine x minus x squared sine x. Running out of space there. Hopefully you can see that. All over 6x minus 2. If I evaluate this at 0, I've got 2 times sine of 0, that's 0, plus 2 times cosine of 0, which is just 2, plus, oh sorry, this was 2x cosine x, so that's a 0, plus 2x cosine x, another 0, minus x squared sine x, another 0. This isn't looking good, guys. All over negative 2, that's okay, so now I just have 0 as my answer. Good job.